Hello, hi, it's me, it's Gustav. I got asked to make a video on how to solve these ray tracing problems, and I saw a lot of confusion within the answers that were submitted for this activity we saw on last Friday, so I'm going to make a video and show you how to solve it. These ray tracing activities, we're going to have a bunch more of them, so it's important to have them down. Um, these diagrams may seem kind of silly or pointless because we do have perfect algebraic solutions. However, it's also really important to get an understanding of what is actually happening with the light, with the mirror, and these graphical solutions do exactly that. We physically draw out where the light goes so we can just get a better, more intuitive understanding. So for this problem, we have an object of height 2 centimeters that is placed 3 centimeters in front of a spherical concave mirror that has a radius of curvature of 12 centimeters. So I'm going to start with my ruler, choose a point. I'm going to make this big because it's important to make these bigs. I'm going to have a 1-to-1 scale ratio. I'm going to just have my radius of curvature start over here at the very end. And I know that that is 12 centimeters away. So I'm drawing a line that is 12 centimeters here. Then I'm going to extend it a little further because I don't know how far out the image is going to go. So my mirror here is 12. My object is 3 centimeters in front, so 9 minus 12 is 3. And it is 2 centimeters tall. So I will try very hard to get 2 centimeters. It's very important to try to be as accurate as you can with these. So this is my h right here. This is 3. Let's extend this down. And this is 12. So another thing we know is that the focal point is equal to 1/2 of the radius of curvature. R here is 6, so F is equal to 1/2. That's a terrible 2. 1/2 times 6, which equals 3 centimeters. 1/2 times 12, which equals 6 centimeters. I can do things. So 12, get my ruler back. It should be right here. That is our focal point. Oops. Focal point here at 6 centimeters. These are all centimeters. A weird thing about these diagrams is that the left is positive and the right is negative. So all values over here are positive, these are negative, and this is 0. It's a little backwards from our normal xy plane, but this is how we do it because we just say that in front of the mirror is positive and behind is negative. That's going to come up later, but I want to point that out now. So, great. Now we can start tracing our rays. So there's a bunch of different ways we can do. First, I'm going to change colors to blue. Our first one, we want it to just go parallel to our plane at the bottom. So starting from H, we go just as parallel as we can. And then it reflects down into the focal point. So my lines are going to get mixed up. See there, I did a terrible job. There's a little bit of, I didn't draw my line very well, so I'm going to erase it and erase just about everything else in the process. But it's important to make sure that our lines are accurate. So this line comes through here. However, so the light comes in this way, goes down this way, but for our for our image, we draw a dotted line here to say that this isn't an actual ray of light, but this is what the ray of light is, in a sense, doing behind the mirror. Of course, behind the mirror, there is no light, but this is what it looks like it's doing. I'm going to fix this up. So that is our first line. Our second one, I'm going to change color again. It comes through R, and again, our the top of our image. So drawing another line, we have our straight line here coming through the top of our image, and then again, now that I'm behind the mirror, I will start doing a dotted line because dotted lines are fun. So now you may be tempted to say, oh, we have two lines intersecting right here. Let's say that that's where our image is. However, no, we need at least 3 lines intersecting. So I will do another one. We have one that comes through the focal point and touches the top of our image. I'm going to do this one in red. So focal point touches the top of our object. I'm going to mess these up, object and image a lot. And then it gets reflected back out parallel to the surface. However, it also, behind the mirror, it looks like it's doing this. So this is pretty convincing. Right here, we have 3 points of intersection. However, you could stop here, but just for demonstration's sake, I'm going to show the final ray that you could draw. So the final ray you can draw, I'm going to do it in black. It comes from the top of your object, and the ray goes right into this intersection of your x and your y axis. Pow! But then it also gets reflected out at the same angle. And as Mr. Leftwich said, one way you can make sure it's the exact same angle is to have a like a shadow realm object below of the same height, and you can draw your line out like this. So what the ray would do is it'll come out like this, but because we're looking at what's behind the mirror, we see everything's intersecting behind here. We can draw our dotted lines, and it's pretty convincing that right here is where they intersect. So let's try to make it as perpendicular as we can. Let's draw it straight down. There we go. Pow. And this is our H prime. This is our S prime. So measuring our H prime, I'm getting, what is that? That's about 3.7 centimeters. My lines aren't very precise because these markers make fat lines. With a pencil, you can go much more precise. And this S prime looks to be about 5.5 centimeters. Now at this point on your activities, I saw a lot of you saying that's close enough to 6 and then going on with your calculations with 6. You don't do that. That is very bad. In the physical world, you use the numbers that you measure. If you don't, then what are you doing? You're not doing any science. You're just, I don't know, doing whatever. So I wrote here that these are 5.5 centimeters and 3.7. Here, this should actually be the absolute value because since we're going in the negative direction, S prime is equal to negative 5.5 centimeters. So this is what your diagram should look like. Again, you only need three rays. A lot of you did 2, some of you did 1, but you need at least 3. I drew 4 just for demonstration purposes, but yes. Great. Now, we can see that the image is upright. It is definitely taller. And it is behind the mirror, so it is virtual. However, it also asks us to calculate the magnification. Now the magnification is equal to h prime over h. Here our h prime is 3.7 centimeters. Our original h was 2 centimeters. The centimeters cancel out, so this value does not have any units alongside with it. A few of you put that it was in centimeters. That's wrong because it's a ratio. It's saying how much bigger did it get? How much does it multiply by? Yeah. So we get our magnification here is 1.85. Yay! I'm gonna box it off because we like boxing things off in physics. And now we'll go to part B. Oops, I pushed the problem up a little bit. Part B asks us to do it algebraically, and the way we can figure this out is through the mirror equation, which is 1 over s plus 1 over s prime is equal to 1 over s. Now, when we're doing it algebraically, we forget everything that we did with the graph. This is 2 separate ways of doing the same problem. So, in this problem, we know what f is, we know what s is, so we have to rearrange for s prime. So that gives us 1 over s prime is equal to 1 over f minus 1 over s, which then gives us 1 over s prime is equal to, what is our focal point? 1 over 6 centimeters. minus 1 over 3 centimeters, which equals negative 1 over 6 centimeters. So then we take the inverse of that, which gives us s prime is equal to negative 6 centimeters. It's negative because it is behind the mirror. In some of these problems, your object will be in front of the mirror, then your s prime will be positive. So great, s prime is negative 6 centimeters. Magnification is equal to negative s prime over s, which is equal to negative 6 centimeters over 3 centimeters. Centimeters cancel out, our negative signs cancel out, so we get 2. Yay! And now our h prime is equal to our magnification times our height, because what is magnification? It is by what factor does a thing get larger? So we can calculate how much larger it becomes. M is 2. Our height was 2 centimeters, which equals 4 centimeters. Yay! That is how you do this. This will get you a 10 out of 10. And something you'll notice is that for our two answers, we have our magnification here equals 2, and our magnification here equals 1.85. Just because you were slightly off with your drawing over here does not mean you will get points off. This is close enough to the actual answer we were looking for, because what we're testing here is not can you draw perfectly straight lines, it's do you know how the light works? And like this answer is pretty close to our answer of 2, so yeah, that's great. A lot of you were fudging the numbers a little bit, making this 3.7 a 4, even though it clearly wasn't 4, and you got a lot of points taken off because that is not conducive of a good scientist or a good engineer, and I know many of you are going to be science or engineering majors. You want to use the values that you get and work with those. And if there's a little bit of error when you're working on something like this, that's fine. Yay! I hope this was helpful, and I'm glad my very ghetto mic and camera setup did not fall. Yay.